Okay, here we're just going to be finishing up the chapter 3 notes here. And so first thing, just to review, these are some ways that we learned that it cannot exist. The derivative does not exist. It fails to exist. It fails at a corner, cusp, vertical tangent, and some sort of a discontinuity. Now here we're going to take it a little further, and we're going to talk about, what about a calculator? How does a calculator find the derivatives on a calculator? Well, on itself, I guess, huh? So we're going to look at that, and it uses this thing called the symmetric difference quotient, where it uses, instead of finding, because your calculator cannot find the derivative, it uses the secant lines, all right, around that point. For example, if we had y equals x squared or something like that, and I want you to find the derivative here, what it'll do is, okay, I have this secant line. These 2 points are equidistant from this point that I want to find the derivative, and so I find the slope of that secant line, then I do the same thing here, the slope of that secant line, and it takes the limit of these slopes and says, well, these slopes are approaching this value for the slope, and so then that's the derivative at the point. So all your calculator can do at best is approximate. This is where it runs into trouble, at a corner. And you ask your calculator, find me the derivative at this point here. Listen, this is what your calculator is trained to do. It's going to find a point equidistant on the left, equidistant on the right, figure out what that slope is. That slope is 0. Same thing. It's going to do it over and over and over again and get extremely close to that value, never equaling that value, hence the term limits. And you notice all of these slopes are 0, but we know that it's not 0. We know that it cannot exist at a corner. And so your calculator is going to give you an answer when we know that it cannot exist. So you have to be careful. Don't trust everything your calculator tells you. So make sure you check it mathematically just to be sure. All right. And then we're going to be talking about this, the difference quotient. So what you have to be familiar with, not only how to use these, but secondly, what they look like, because these are all different ways to find the derivative. This one, f of x plus h minus f of x all over h, this one we're familiar with. All right, you should already be familiar with that one. It's this one that we're not necessarily familiar with right now. We're going to use a little bit in this section and in these notes. Okay, so that's the one we're going to work on. And so just remember, you know, what it says here, symmetrically on either side of 0, like I said, so it's going to wrongly calculate. Don't believe your calculator, everything it tells you. Differentiability implies continuity. So if I tell you that a function is always differentiable, that implies that it's always continuous. Okay, like if I say, here's my function. This function right here is always differentiable. What that says is there's no breaks in this function. Okay, there's no breaks. Therefore, it is continuous. You know, if it's continuous, then I can trace it without lifting up my pen. Something like this is not continuous because to go from this point to this point, I had to lift up my pen. Okay, so that's not going to work. Now, this does not go both ways. What I mean is, yes, differentiability implies continuity, but if I tell you that a function is continuous, that does not imply differentiability. Because look, this function right here is continuous. I hope you agree because I was able to draw that without picking up my pen. However, it's not differentiable at this point, so that doesn't imply that it's always differentiable. All right, so it goes one way, not necessarily the other way. And then the intermediate value theorem for the derivatives, it says basically if A and B are any 2 points in an interval on which f is differentiable, then the derivative takes on every value between f prime of A and f prime of B. So here's A, and here's B. So let's say this function does something like this, from A to B. Now, f prime of A, that'll be in red. Here's my slope, or my tangent line for f prime of A. That's the slope. So let's say this slope is 27. Whatever, I don't care. F prime of b, that's this slope. Let's say that is negative 27. Now, what the intermediate value theorem for derivatives says, first of all, if this is differentiable everywhere, meaning it's continuous, differentiability implies continuity, if I take every single slope in here, okay, from positive 27 to negative 27, they are all accounted for. So I know some point between A and B has to have the slope of 0, okay, right around here. I know that some point between A and B has to have the slope of 10 or 12 or 12.27654 or 3.826979, 10, 12, you know what I mean, right? Every single point. That's what the intermediate value theorem for derivatives says. Okay, so with the intermediate value theorem, it's mostly just like an existence saying, hey, this has to exist. There's not much that you can do with that, except they can ask like very abstract questions. How do you know this exists? Or how do you know that exists? Or what is this? How do you know it has to have this slope? And you're going to use the intermediate value theorem to say, hey, I know this has to exist because of this intermediate value theorem, which is an existence theorem. That's why they're called existence theorem. And throughout the year, we'll have several of those. On this problem, we're going to do things the way a computer, your calculator, does them, and we're going to use that symmetric difference quotient here. All right, so it says find the numerical derivative. So in this homework, quizzes, tests, whenever you're asked to find the numerical derivative, this is what you're doing. All right, so you go back to the symmetric difference quotients. Okay, if we go back to that real quick, there it is. It's f of x plus h minus f of x minus h. This h, remember, okay, is that distance between on each side. So if it's an error of 0.00001, then it would be plus 0.0001 and negative 0.001, whatever it is. But in this problem, it's just 0.001, thankfully, right? And so it's going to be f of x plus h. So it's going to be 4. We're going to plug x plus h in here. We're going to leave that blank. Minus x plus h quantities squared minus x minus h. So it's going to be 4. I'm going to leave this blank. And we'll come back to those in a little bit. All over, if you look at the symmetric difference quotient, it's all over 2h. Now, up here, you notice I just rewrote these. Oh, that should be a squared. I just rewrote them. Now, inside, this is x plus h. X is 3, h is 0.001, and so it's 3.001. Over here, it's x minus h. So this is on the right side of your point, and this is on the left side. So what you're doing, all you're doing is you're finding the slope of the secant line. All right? So this is 0.001 to the right of the point, and this is 0.001 to the left of the point. And so then that would be at 2.999. And then down here, it's over 2 times, because it's the distance, so it's just double, 0.001 times 2. Okay, so that's the first step. Then we punch all of this into our calculator, la-di-da, la-di-do, and that gives you the answer of somewhere really, 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 really close to -2. So that's the slope of the secant line, really, 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 really close to x equals 3. And that gives us the approximation of x equals -2. And if you found the exact slope, it would be x equals -2. But if you put this in the calculator, depending on your calculator, you might have gotten like -2.0000001 or -1.9999999, but either way, it's something really close to -2. And that's what your calculator does. It just rounds to that number, what it's approaching. But it would probably use even smaller values for h, since it can compute those really fast. Okay, so in this section, let's just review really quickly how things cannot be differentiable. That's what we're looking at a corner, at a cusp, at a vertical tangent, and also at discontinuities. Extremely important to understand that. Okay, then we talked about what's it mean if functions are local linear, if they are local, they have, let's say, the property of local linearity. Well, that means they are differentiable. If you zoom in on a point so much that it becomes a straight line, then it's differentiable. If not, if it doesn't straighten out, then it's not differentiable. Then we talked about this. This is what your calculator does. This is what we did before. Okay, you need to practice this one, okay, so you can see where those errors come from and know how to do that. Differentiability implies continuity, and then we did a couple of problems. All right? So, let me know if you have any questions in class, and we'll see you then.